In the previous video, we did the molecular orbital energy diagram, bond order, and electron configuration for hydrogen H2, hydrogen gas. Now let's do it for helium. Our picture starts with our energy arrow. It starts with a helium atom. Well, let's just draw it in. A helium-2 molecule in the middle, and a helium atom on the other side. We draw the basically the orbital energy diagram that we've done before, no M, but we drew the orbital energy diagram for each helium atom. Each helium atom now has 2 electrons. And we said that in making molecular orbitals, there's one sigma 1s, which is the bonding molecular orbital, and then equally higher than the 1s's is sigma star 1s, the anti-bonding. And again, we can connect them up with dashes. And this time, when we place the electrons in, we still place them in the lowest energy position first. 1, 2. But we have 4 total electrons. And so we do fill the anti-bonding molecular orbital. What that means is when we calculate our bond order, which is bonding electrons minus anti-bonding electrons divided by 2, we get a bond order of 0. And what a bond order of 0 means is that that there's no bonding, for one thing, and no bonding. And further, molecular orbital theory predicts no bond or no He2 molecule. So MO theory predicts no bonding, no He2 molecule. And that's nice because now we can start to make predictions, not just, okay, we know we have a formula, let's start with the formula and then draw the Lewis structure. MO theory is much more powerful. Now, more things we can say about it. Well, let's actually do the electron configuration for helium-2, or what it would be. So the electron config would be sigma 1s2, sigma star 1s2, and you can start to put things in parentheses if you'd like, so that you know, can separate the star from the 2, or the asterisk from the 2. Okay, now bond order. So if the bond order is greater than 0, then molecular orbital theory predicts the molecule will exist. Also, as bond order increases, stability increases. And so stability, let's put a colon here, colon, sideways colon, colon, stability increases, bond length decreases, and bond strength increases. And this is nothing new, because we've talked about this as trends that we've seen from drawing Lewis structures, with a double bond being shorter and stronger than a triple bond, and so all those trends still apply to molecular orbital theory. Let's see. Yeah. We'll also see non-integer bond orders, and that's okay too. although that's different. Well, let's say we had to handle non-integer bond orders with resonance structures and Lewis structures before. Okay. Now it's time for one of the pieces of evidence that proved or really showed that molecular orbital theory was more correct, and in fact it is entirely correct now. This is going to be the same molecular orbital energy diagram, bond order, and electron configuration for oxygen, O2. And this one I've got a pre-drawn picture here, so let's zoom in a little bit. And let's actually zoom in a lot. There we go. So we haven't even drawn the 1s's because 1s's are core electrons and they will not participate in the bonding. We're starting with the 2s, and so on the left here, this time with boxes, there will be an oxygen atom. On the right, there will be an oxygen atom. And in the middle will be an O2 molecule with all of its molecular orbitals. And let's see, yep. Oh, it says AO, AO, atomic orbital, molecular orbital here. And it also says that these are the molecular orbital energy levels for O2, F2, and neon 2. And there's a different, slightly different diagram for the other elements, the other diatomics, carbon, nitrogen, and I think beryllium. But the process is the same. Let's go ahead and put, for oxygen, it's 2s2, 2p4, 1, 2, 3, 4. Same thing on the other side. And what you've got to be able to do is now place, so if I give you this layout and you have to be able to put the electrons in, I will point out that this is sigma 2s, so a bonding molecular orbital made out of 2s atomic orbitals. And that's a little asterisk there. I'm not sure if you can see it, but I'll make it bigger. You can tell the ones that are bonding molecular orbitals because they're lower in energy than the atomic orbitals. Furthermore, here's our anti-bonding ones up here. And you can see that of the 6 2p orbitals, 3 of them are bonding, 3 of them are anti-bonding. Anyway, let's go ahead and put the electrons in. 1, 2, 3, 4. These are the 4 electrons down here. Now we have 1, 2, 3, 4, 5, 6, 7, 8. Let's go 1, 2, 3, 4. Notice we're putting 1 electron in each before we pair them. Still a thing. 5, 6, 7, 8. And if we do, now we can, well, let's keep it right here. And let's move it over a little bit. The top of the page says do an MO energy diagram, then do bond order. Bond order here is going to notice that there are 2, 4, 6, 8 bonding electrons. Let's see, there we go. There are 1, 2, 3, 4 anti-bonding electrons. Divide that by 2, and you get a bond order of 2. And that is exactly analogous to doing the Lewis structure and coming up with a double bond between the 2 oxygen atoms. Now what's missed here, and actually I guess let's do the electron configuration. Sorry, give me a minute. So this is going to be sigma 2s 2 sigma 2s star 2 sigma 2p 2 pi 2p, and these are going to be pi 2py. It doesn't say this on here, and we'll talk about this in a minute. Pi 2p y 2 excuse me, pi 2pz 2. Then pi star 2p, and I guess, oh, yeah, no, I caught it. Sigma 2p. I guess we should call this sigma 2p x. And again, continuing on, so pi star 2p, and that's going to be y squared 2. Pi star 2pz. Oh, sorry. A little distracted here, I think. Pi 2py is going to be 1. Pi 2pz star 1. There we go. Now, for the pièce de résistance, is this paramagnetic or diamagnetic? Well, we'll do an extreme zoom in here to the 2 electrons that are unpaired. Unpaired electrons means that oxygen is paramagnetic. And it turns out that oxygen, O2, is paramagnetic. And that was one of the pieces of information that solidified molecular orbitals theory and its ability to make predictions and be correct in general. Let's see. One other thing I wanted to do, I wanted to talk about what is a sigma 2p versus a pi 2p, at least for the bonding molecular orbitals. For sigma 2p, if you're ever asked to make a sigma 2p orbital, remember that 2p means you're going to be using p orbitals. Sigma means that when you bring the 2 orbitals together, that the electron density will lie between the 2 nuclei. And so here's our area of overlap. And so sigma means we add. And so adding these up, we would get something like this. A fatter part in the middle, still not touching the nuclei, but the outside parts stay the same. Sort of looks like a little piece of candy. If we were to do the sigma star 2p, there would be a node right in the middle here. Now pi 2p. For pi 2p, well, these are going to be too far apart. Let me try it again. So pi 2p, you're going to have to take these 2 p orbitals. And again, where they overlap, you're going to get adding. And so our answer here is going to be something like this. So where they add, it goes up. And I'm always much better doing it this way, so it's, I think. Something like that. So this is going to be pi 2p, molecular orbital. This is going to be sigma 2p. And the process is always the same that we've done before, which is take the orbitals, smash them together. Where they overlap, make it bigger. And I think I exaggerated the bigness of it there. And then if we were to do star antibonding, there'd be nodes right halfway between the 2 nuclei. Okay. One last thing. We said you could have 2 atoms, but the atoms have always been the same up until this point. Now we'll make them different atoms. These are going to be, this is going to be for nitrogen monoxide. And for this, it's going to be, well, you can see that the S's and the P's are different levels. So whichever atom is more electronegative, that's going to be oxygen, will be lower in energy. And another way of thinking about that is that the atom that's more electronegative is also going to be smaller. It's going to have its electrons pulled closer to the nucleus, and those will be lower energy electrons. We also have our nitrogen atom, and these are going to be 2s and 2p. So for oxygen, 2s2, 2p4. For nitrogen, 2s2, 2p3. And we've lost some of our designators here, but we still can see that they're connected and which orbitals go with which. Now this is going to be the NO molecule in the middle. And again, we just put our electrons in. We have 4 electrons down in the 2s area. 1, 2, 3, 4. We have 4 and 3. We have 7 electrons here. First 2 and the lowest one. 3, 4, 5, 6, 7. Until you run out of electrons. Now, bond order for this. We have 1, 2, 3, 4, 5, 6, 7, 8. Bonding electrons. We have 1, 2, 3 anti-bonding electrons. Divide that by 2 and you get 2.5. And this is still paramagnetic because there is one unpaired electron. And the bond order is 2.5, and that's a relatively, predicted to be relatively stable species, even though it has an odd number of electrons, something that Lewis structures would find hard to deal with. Now, I said that we will only be seeing molecules with up to two atoms. I guess no, less than that. It's got to be a molecule, right? But on exams, but it is a much more powerful theory than we use it. We're just introducing it in this course. And you can start to see that you get truly molecular orbitals even when the ion, or the species in this case, has 4 atoms, even when you're dealing with something like benzene, C6H6, it turns out that benzene has p orbitals, where if we were to draw the skeletal structure for benzene, we would draw double, single, but those sets of double bonds, which are pi bonds, actually make a pi molecular orbital that's over the entire top of the molecule. And that is why you will often see benzene drawn with a skeletal structure with a circle in the middle to indicate those that molecular orbital, those electrons being in a low energy position across the molecule. So it is a much more powerful theory than we get to really get to, but we'll start.